Again, I apologize for my voice. Things have not gotten better.
I can hear it today.
Today, you're going to find is a culmination of things you've learned over the last month or so in here. It's one of the best applications of AP because you can look at a solution, you can look at something being added to it, and then you can use all the skills that I've tried to put into your brain to figure out the best way to analyze it. It's really good real-world chemistry because if you have a solution, and let's say it already has a buffer in it, and you go and you add some strong species, you can use these skills to use what you know about strong species, use what you know about buffers, and figure out exactly what will happen. Or if it's not a buffered system, maybe you add it, and when the reaction is done, all that's left is salt. Well, then your brain goes, oh, I know how to analyze salt. You do hydrolysis. And then through hydrolysis, I could figure out the pH or POH and go down that road. So because of that, you're going to think that today is clunky. And what I mean by that is there's a high probability that some of the invasions that we're going to look at will frustrate you. So what I need you to do is be patient with yourself. Probably definitely watch this lecture again so that you can keep up with the subtleties of the steps. Now, I 100% will not finish this lecture in time. So I'm going to do what you've seen me do multiple times is I'm just going to keep going. So as the bell rings and you eventually leave, just please do so in a somewhat quiet manner to not disrupt third period, they all have to watch the video for sure because they didn't get to see the last two problems. And then of course, if you don't stay or whatever, then watch the video so that you can see the additional examples. And again, I'm sorry. I've canceled all of my talking in pre-AP.
Good. I feel like I'm always having an advantage going on because
I can't cancel it for y'all though. Y'all are too important. Okay. So here we go. Shh. What an invader is it's when a strong sample is added to an already established solution. The thing that makes these work differently from each other depends on that already established solution. Depends on what was in there. So what we have to do is be able to think chemically about all the stuff that we know about acids and bases to figure out exactly what must take place as the invader invades. Now, the thing about these that also makes them different from each other is who's going to win during the invasion. You'll see there's an analogy on your slide that refers to it being considered like a war. All right? You're going to have a solution. You're going to have it's going to always be a strong sample, invade, and you're going to figure out who wins. Now, guess who you're cheering for. Do you think you're cheering for the underdog or for the strong guy? You're cheering for the strong guy. Because it turns out, anytime that strong guy wins, there's no chance of hydrolysis. There's no chance of a rice table. Because as you already know, any time so far that I've asked you to analyze a strong species, you pretty much just have to take the negative log and go on with life, right? It's been the weak species and the salts that have required all those additional steps to find concentrations and pHs and POHs. So you are cheering for the strong to win because when they lose and the other guy wins, that's where the extra, sometimes lots, of hidden steps are. What you'll notice on the next slide is something that I'm not going to go into. It's a summary of trying to summarize everything we've done over the last 2 units. I'm not even going to refer to it, but look over it and maybe it's helpful to you, maybe it's not, but I was trying to give you as brief a summary as I could on some stuff that we've done that will apply to invaders. If you would, please cover up the bottom part on all of these. And we are going to dive in. If you look at this problem, you'll notice the hydrochloric acid, which you know is a strong binary acid, I bring clay, is being dumped into a buffer. Now this problem's nice because it's telling you it's a buffer. you will run into problems that end up being a buffered system, which of course is a weak acid or base with its conjugate also in there. You'll run into them that it doesn't tell you that it is. So I'm trying to start us off with the easiest version of anything that could be easy. But we know that we're going to be dealing with a buffered system at the end. But none of that matters yet. We need to talk about that strong species that is invading.
For buffers, since it's going to be a weak acid or base, the conjugate will also be weak, right?
Correct. Okay. And the way that you know that it's weak is its parent is weak. Is it? Because remember, that's how we always analyze salts. Because if you remember, the conjugate is always attached to a salt, and it'll be the species that comes from the weaker parent. Okay. Here's step one. The moment you know you're dealing with an invasion, no matter what kind of problem it ends up being, we're going to take the strong part of the strong invader and add it to the solution. So in this case, the H plus is what's invading. So this first step is always going to be H plus added to something or OH minus added to something because it's strong. Now, this is a buffered solution. Think back to yesterday. Think back when I said that we were going to dump stuff into your blood. If you remembered, when it tells you that it's already an established buffered system, remember the H plus isn't going to interact with both of the items in there. It's going to interact with one of them and make it produce the other. Remember, that's how the buffered system worked. So if we look at what is in this solution, it looks like it is acetic acid and sodium acetate. All right, well, what would the H plus react with? Would it react with the acetic acid or would it react with the acetate? Now, in the corner over in the margin of your notes, I need you to familiarize yourself with these abbreviations. This is not actinium, all right? This is an abbreviation for acetate. It's a shorthand. So this is HAC, which is acetic acid, acetate with a hydrogen in front of it. And this is AC minus acetate, just floating around. Now, if you're making that note in the side of your notes, remember what acetate really is. All right, this is acetate. So acetate shows up so often in real life chemistry that this is why chemists made up this abbreviation basically, is to shorthand it when they're doing calculations and stuff. So I invite you to shorthand it because that's an annoying polyatomic ion to have to write a bunch of times.
What does the AC mean?
Acetate.
So what's the HAC?
That's acetate with hydrogen in front of it, making it acetic acid.
HC2,
Right, exactly. Yes, it would be that, which is acetic acid. All right, anyways, so.
what do you call the one with the ions? Like acetic acid ionized?
Polyatomic ions.
Funny.
So, which item is he going to interact with? Well, I would argue that he's going to interact with the negative ion. All right, he's going to interact with the acetate. And this initial invasion is always going to use a regular arrow, all right, not an equilibrium arrow because it's always a strong species that we will be analyzing in the first step of any invasion problem. Okay, so if these guys react, of course, the whole point is to produce the other part of the buffer, right? Remember, when you're dumping the acid into your blood, you want it to make more of the basic guy. If it dumps base into your blood, you want it to make more of the acid guy. That's the whole point of the buffer. It tells you it's a buffer. You could have predicted this would happen. So we dumped in acid. It interacted with the AC minus and produced the other thing that's already in your blood. Well, this isn't blood, but the other thing that was already in the solution, acetic acid. Remember, what we are wanting to figure out, though, is who's going to win the invasion. And there's values, there's numbers of each thing, so you can figure out who's going to win what. We're cheering for the strong, but if the weak wins, there'll be quite a few steps. The way that we're going to figure out who wins needs to be based off a limiting reactant kind of mindset, all right? Basically, you're looking at the amounts of the stuff you have, and you're going to figure out, well, who gets used up first? That'll be the loser, the guy that gets used up first. But if we're going to compare two substances based on a limiting reactant type way, what units do our values need to be in for that to happen?
Moles.
Moles. Remember, the only way to compare two different substances is a mole-to-mole comparison. if you look at the values that they gave us, we've got volumes and concentrations given. Don't write this down. I just want to remind you. Here is the equation for molarity. Do you agree?
Yes.
If that's the equation for molarity, and I'm telling you to figure out the winner, we need a mole comparison. What would I want to do mathematically to molarity and liters to get moles?
Molarity times liters.
You multiply, all right? Now, if that went over your head, then you need some work on your period algebra, all right? But this times this equals that. That's super important to know for this because usually most of the invader problems give you these two items, and you need moles in order to figure out the victor. All right, and I know you think it's going to be me because of those, but it can't be me. The big my biceps. Okay. I get it. It was a joke. Okay. So, in order to find, for example, the H plus moles, molarity times liters. All right, and it gives me them. All right, now it gives me milliliters. So I'm not going to do it times 125. I'm going to do 1.125, all right, times, and this is over in the margin of your notes. I wouldn't put it below the HAC, all right, times the 0.525. Does everybody see why I'm doing this? Everybody see why I'm multiplying those two numbers?
Yeah.
All right, I want moles of him, all right? So I'm going to go 0.125 times 0.525, and I'm going to get to the proper sig figs 0.0656. And that's my H plus mole count. I want to compare that to the mole count of the other dude, which we'll find in the exact same way. No, that's bad news. So we're going to take 0.125, all right, just because it gives me coincidentally the same volume, all right? And what was his molarity? What was that guy's starting molarity? Find it. 1. All right, times 1. All right, so that one was kind of boring. We have 0.125.
Would it only be one sig fig then?
Yeah, don't. And there's a couple problems here that are doing that. I'll never do that to you on purpose, the one sig fig thing. All right, 1.00. I'm sorry. It's going to be frustrating during this lecture that they're written like that. I didn't catch it when I was writing. My bad. Okay, so guys, we haven't really done too much yet. All right, we took the strong guy and added it to the person that he's going to interact with, and then we found the mole counts of each. Are we okay? Now,
In the first one, why did you use 125 milliliters and 0.25 to get the molarity of it?
because the H plus is the HCl.
Oh, it comes from there.
Exactly. That's the strong intruder. It's just the chlorine isn't going to have any effect on what we're doing here. It's not going to interact. All right? And we don't start with any of him. Now, remember, we're going to figure out, now we have moles. Now we can do a direct comparison and figure out who the limiting reactant is. It's just a smaller number. You know how to do that. Which one of those dudes is going to be used up first? Now, that's bad news because the strong is going to lose. So, anyways, the smaller number. We want to subtract the smaller number. And it'll show that he gets used up. All right? Of course, we want to subtract it from this guy too to find out how much of him is left. So to 3 numbers past the decimal, I'll go 0.125 minus 0.0656, and I'm going to get 0.059. Now, think about the shift, though. While, of course, the reactants always go down, what do the products always do? They always go up. So we do have a value here to show the amount of moles that will increase on that side. All right? So now I've shown that the strong guy loses, and we have an amount of acetate and acetic acid floating around in the solution. Now, hey, look, it proved that it's a buffer. That's a weak acid, and that's its conjugate. So it's definitely a buffer. What does the question want to know? pH. How do you find the pH of a buffer? Henderson-Hasselbalch, right? That's what we did all day yesterday, was this. Now we've got the information that we need. Well, almost. In the HH equation, the Henderson-Hasselbalch, we need the molarities at the end, right? The molarity of the ion divided by the molarity of the acid or base. That's how the equation ends. What do I have here? Ooh, moles isn't good, all right? Is it easy to turn moles back into molarity?
Yeah.
Yes, of course, it's very easy, all right? Because moles divided by liters equals molarity. We already talked about that equation once, all right? So I want to divide both of these by the total volume. Don't miss this. What's the total volume?
250.
0.250. All right, we mixed them. All right, just read through the chemistry. Remember, it's all real life stuff. They're not trying to trick you, but apply it to the lab. All right, they had 125 mils. They dumped in 125 mils. My final solution after this is all said and done is 250 mils. All right, and this, all right, and so this is liters. So moles over liters is going to give us the molarity of each. All right, so the acetate molarity, 0.059 divided by 0.25, is going to be 0.24 molar. All right, 0.24 molar. While the acetic acid is going to be 0.0656 divided by 0.25, which is going to be 0.262. That'll be the concentrations of those guys at the end, 0.262 molar. How are we feeling? By putting 125 mils plus 125 mils. All right? And now, this should be just such child's play. All right? Hey, by the way, I looked on Schoology, and every single problem gives you Ka and Kb. Remember we talked about yesterday that you have to go find it in a chart? There's only one problem in all of the assignments that make you do that. All right? So, it's not too terrible. But anyways, I will let you know that the Ka here that we would have found is 1.8 E negative 5. Now I'm second guessing myself. Yes. Is 1.8 E negative 5. So now with all this information, we can just finish the problem. HH equation says that pH equals the negative log of 1.8 E negative 5 plus the log of the ion concentration over the weak concentration. So just make sure that you don't get them mixed up. All right, it's going to be 0.24 over 0.262. Yep.
Why does it have a Ka? It's not in equilibrium.
We're running off the Ka of acetic acid, the published Ka. You're right. This equation does not have an equilibrium. It is not equilibrium. You're absolutely correct. All right. But what we're analyzing is the constant value of HAC at equilibrium, because that will spit out the proper pH. Because this equation is done. We don't care about the reaction. We just care about the solution that's left over. To 2 sig figs, I get 4.71. That was fun, right?
You made it seem harder than what it was.
I did? I try to take credit for the opposite. What would you have had me do? Go faster?
Dear God. It wasn't as hard as you made it seem like. I mean, it's
Yeah, you said it was going to be clunky, and I was like, yeah.
No, I agree. Hey, if I'm wrong, can I erase?
Please make it harder.
That's what it sounds like. That's what I hear too.
No.
Y'all know my job is not to make anything difficult.
When you're teaching those five, the one we're doing by ourselves, I'm like, what?
Yeah, for some reason I can't have any problems. I mean, someone's like dyslexic.
I'll write the words backwards next time.
There we go.
Can you show me my next problem? Now, of course, it walks you through with all that wordy at the bottom. I don't know if that's helpful at all, but I try to pretend.
You okay?
The sig figs are all messed up here. All right, let's assume that your volumes go to 3 sig figs again. My bad. All right, so different situation here a little bit. I do see that it's an invader because it's a strong species being added to a solution, but the solution is not self-identified as a buffer. All right, so we need to. It doesn't mean it's not going to be a buffer. It just means that we will definitely want to finish thinking through this. Isaac, I want to throw it against the wall and watch it break. It'll be exciting. What's up?
Will we ever get in an equation a weak base or acid, like in the problem?
If you do, then it would be analyzed the way that you find a weak pH acid, which is just a rice table, add it to water and do a rice table. It wouldn't be an invader problem if that happens. Okay, hey, what's the first step in an invader problem no matter what? Take the strong species and add it to what it's being added to. So my strong species this time is OH minus. And this isn't a buffer situation where it's only going to mess with one of the parts to make the other part. It doesn't say that. It just says we're adding it to acetic acid. All right, so let's add it to acetic acid with a normal arrow. All right, remember that's just acetic acid. I do not want that to be the reason that somebody gets confused. All right, this is not H bonded to the element AC. This is H bonded to C2H3O2.
Can you put that instead of abbreviation?
No, because I'm teaching with acetate in every single problem today, so I'm not going to do it. All right, so here we go. Now, as I predict, this looks like a classic Bronsted-Lowry, in which case I know that the OH minus wants to gain, while the HAC wants to lose. Now, I can see that this has the potential to be another buffer, all right? It's got the potential to be. I don't know what's going to be left in the solution, but I see a weak acid and his conjugate, so it could be a buffered system. But let's work through and see what the numbers do. I need to know who wins, which means I need to find the limiting reactant based off moles, all right? For the NaOH, I'm going to go 0.125 times 0.500. And I'm going to get 0.0625 moles. Yeah, I said that we are adding the. I said that twice. That we're fixing the sig fix.
You have to write it down.
Yeah, write it out.
To find the HAC, I'm going to, hey, look, what do you find curious about the other values?
It's the same. Oh, snap.
It's the exact same.
Wait, can there be a so then it's buffer?
Can there be a stalemate?
You're gonna have what's it called?
A tie. I'm just kidding. I know, that's not the word you're looking for. Now, while this looks like it might be better news than the last one, it's not. All right, it's only good news if the strong wins. Here, they're gonna get used up at the exact same time. All right, it's like, remember my cake analogy last year when I taught you limiting reactants? This would be having the exact right amount of ingredients. And if you have the exact amount, I can talk, I can't. If you have the exact amount that you need, then you'll use all of it up, right?
Yeah.
So we'll have to subtract the smaller number again. But this time, it's the same number. Yeah, we're going to run out of both of them. All right? But it's minus plus, of course. Right. Y'all are you will ignore water forever. And well, water has no bearing on pH. It has bearing on buffer capacity, but it's got no bearing on pH.
Water is kind of overrated.
Is that a rice table?
No. All we've done is limiting reactant. All right, I found the limiting reactant and I made it affect everything the way that it would. It'll make all the reactants always go down, products always go up.
Nice.
All right, if it was a rice table, there'd be X's somewhere.
There's a big X. Big ol' X. What do you mean?
You know what I mean.
Oh, like X value.
Yeah, we're not going to solve for that ridiculousness.
It equals 0.
It's mega X.
All right, guys. Now here's what you're not going to like. Focus on my words on how I look at this now. Is it a buffered system?
Yes.
No, because we do not have both. How much of him left is there?
0.
None. All we have is this ion floating around. Now, from last unit, if all there was left in a solution was an ion, what we did, they're making fun of me. What we did was we assumed that if we were going to analyze him, that he would have a weak parent. And if he did, we used hydrolysis.
He does have a weak parent.
He does, exactly. He does have it. And in these situations, they always will, if this happens. Right. The only thing that we have left is the acetate ion. His parent was acetic acid, carbon-containing acid, which makes him weak. Therefore, the only way that we can analyze it to find pH now is hydrolysis.
Ooh.
Right, it's only a buffer if you have an amount of the weak acid or base with its conjugate. We're missing one of those.
Literally, carbon emissions over there.
So, how do you find the pH of a salt? You add it to water.
Wait, so acetate is salt?
Acetate's parent was a salt. If you think back to any of the hydrolysis problems from last unit, you never put the entire salt into the rice table. It was only the ion of
Okay,
it.
so I'm sorry for confusion, but like, isn't his father acetic acid though? So like, how is that making a salt? Are acids salts?
There's two parents, buddy.
No. He's got a point. The moment that we figured out it's not a buffered solution, really there's only two other options. We can analyze it as a weak acid or base. All right. Well, that's not a weak acid or base. It doesn't have the OH or the A. It doesn't have any way for us to analyze that. And if it's neither of those, if it's not a buffered solution and it's not a weak sample that you know that we've analyzed last unit also, then you're going to do hydrolysis.
Just because.
So because the acetate can be bonded to any metal to create salt. So if you're looking for an absolute, that would be the best thing I can help you out with at this point. If you look at what you have here and you know it's not a buffer because you're missing something, and you know that what you're left with is not obviously a weak acid or weak salt in its form, then we need to do hydrolysis like we did last year. Now, if we remember and now this is there's nothing new now. We're just going to do a hydrolysis problem together for fun. So, we know that if we go Bronsted-Lowry here that we're going to end up with this. All right. And of course, if we're doing hydrolysis, this absolutely is a rice table.
Period.
It's a rice table.
What?
You mean ice table. Yeah, you mean ice table.
Awesome rice. More like a just say.
Now, there's some more terrible things, guys. What does I stand for?
Initial ice cream.
I wish. I like that guess.
Initial rates.
No, initial concentration.
You went back to kinetic.
Initial concentration.
Initial concentration. All right, what do I have though? What is this?
That is moles, boy.
We need to do this again.
Moles is no good. Guys, we need a concentration here. All right, but we know that moles divided by liters is a concentration. So what do I need to divide 0.0625 by?
0.125 milliliters. Why are we doing? Oh, because combined.
Because we mixed them together.
Yes. Period. Okay.
All right.
All right. you're not divided by 2.
So, right here, I'm going 0.0625 divided by 0.25, and you actually end up getting 0.25.
Wait, when you're dividing it, you have to divide it by the product.
Well, it's the only number I have left.
I know, but like if it wasn't.
It depends on what you're analyzing. They're totally connected. I'm analyzing the AC minus. This value is directly connected to the acetate ion.
Okay.
How does he make up the whole solution?
What's that?
How does acetate make up?
It doesn't. So if you remember back to the last unit, this was a workaround to figure out pH. All right. So
technically in there at the same time.
right. And some of this is theoretical chemistry that you can apply to the lab to get the absolute right numbers in reality. All right. What we're doing is we're theoretically adding acetate to water. All right. And whatever we get from our workaround here would connect to a pH meter if we were to test it. All right. So some of y'all I see are working ahead of me in your rice table.
Yeah.
All right. So all of this should look familiar.
And the reason why, just to make sure, is the minus is on the reaction side because while the reaction goes down, the products go up.
Yep. Always.
Always.
I mean, not always. In equilibrium, you can prove that it'll shift left, but if it doesn't indicate anything, then we always go this way.
Not always.
Quiet, please, guys. I can't hear.
Molarity of acetate that you got, that's to be class 250.
That divided by that equals that.
What a coincidence.
What a coincidence.
All right, what do we do next?
We keep going. Now, again, there's a constant value that you need. All right. Now, it's hydrolysis. See, so they pointed out that we need Kb, but of course, what are they going to give us?
KA. How do we solve for KB?
You did 1.0.
like to speak.
It's kW over.
Oh, KW over K.
Yes.
And then it's vice versa for KB, right?
School is
So
I'm not thinking about it. It's a real
Mr. Cummings.
Do you get 5.6 E negative 10 there? Yeah. What's up, Isaac?
So if it were to give us KB and we need to go to KA, we would just do like the same thing, just like vice versa with K and KB.
Yeah, but the negative 14 is always on top.
Okay, cool.
I'll have to talk to the CEO.
It's KW over KB.
Right.
Or no, wait.
Yep, that's right. What you just said is correct. And now we can finally solve. Told you it was bad news.
Now it's a fun.
No, that's just your brain.
This is only problem 2. I don't like how long these problems are.
Shoot, you don't need to go stuff from here, you guys.
Your test right now has 7 questions on it.
What?
Guys, I have to find a balance. This is a tough unit. I know it's a tough unit.
Maybe we should just do one question. You fail, you pass with a 100.
I'd rather have
Theoretically get a 0. This is
That's a way to get
Stop tweaking.
Keep going, guys. Come on. Time's against us.
Okay, I apologize, sir. Where'd you get the X squared from?
Corrected.
Oh, because.
X times X. Remember, it's the products timed each other over the reactants timed each other, but there's only one reactant. Come on, keep working, guys. Keep working with me. Stop me if I do something that you don't understand.
Gabby.
Oh,
the other
It's always Gabby.
You're missing the testing.
Relax, y'all. Be nice to your brain. Do not let this stress you out. It will take practice, but you can do it.
Maybe we should start doing mindful minutes in here. I do mindful minutes all the time. Oh my god. Engage your space. Shut up. I'm telling you, that's how it goes. Hey, y'all, you're
Yeah,
on
Diego.
government next year.
Why do you need KB if the rice equation has an acid?
no, but
Oh.
once you see
Yeah.
OH, you
It'll always happen if it's hydrolysis. Every time.
Wait, what's gonna happen?
that you have to do this conversion. You decide it's a salt.
I'm gonna stay
Always.
here for a while.
Quit making that sound.
There's too much to remember. Stop talking.
There is a lot to remember, but you can get college credit in this class, remember?
I'm state exams.
So,
That's why
I'm in here for dinner. It's the only reason I think
it's just
I'm in
that.
here because he said
Trust me, guys. That's what my mom.
What's the only reason you took this class?
you whenever you tested everyone, you were like, yeah, I teach AP Chem. I didn't realize it was like continuing.
I took this class for a challenge.
You didn't realize it was a continuation? What did you think the class was?
I thought we were
Just a
doing the same
review
thing
and
from last year.
preview.
Just
Yes,
like more in depth.
Is it really? That's crazy.
I didn't realize we were doing like sick.
It's basically
I thought that was it.
Chemistry's never ending, darling.
There's a lot of stuff that you lied to us about.
It's all about the Bible.
Oh yeah, this isn't true.
Alyssa said this blank and this blue.
Hey, did y'all get 1.14 E negative 5 here?
No.
What?
I don't know. I'm trying to concentrate.
Okay.
I got 1.2.
No, don't get that. We gotta go to 3 sig fig.
No, but like they only give me.
What? That's great. Alright. Wait, what did you get?
Solving for.
Exactly. And that's where you gotta be careful. Make sure you're tracking your numbers because we're not done.
Wait, I got 1.8.
That's the concentration of OH, so now we just gotta do the POH equation now, right?
Well, but it wants pH.
Oh, and then we get used to it. So what you need to do is
All right, so I've got a hydroxide concentration now, but I need to get to pH. There's a couple routes from here. All right, but what I would prefer to do is go negative log of that number to get POH, and then it's pretty easy. So if I go negative log of the 1.18 E negative 5,
Is this the last step?
Yes.
kind of.
No, so we have to do 14 minus.
All do you know is if any of those?
Guys, it's already 25.
And it's going to give me 4 points, ouch, 928.
You're so good. Just tell me every time I put your stop pencil.
So if that's POH, how will I arrive at pH?
Subtract by 14 and then it's 9.071.
Guess what we're going to end with, people? An answer.
9.072.
Yep.
an answer to the equation.
I got lost.
9.072. That's what I got.
Mr. Cummings sidetrack.
Smooth grooves.
No, we found
I know, I'm sorry. I did not invent chemistry. What did you say? I'm going to still be teaching during lunch. Y'all, I'm trying to. I need to quit talking. I'm going to collapse. All right, let's keep going. Let me show you one with the strong winds. It hurts. I did this 14 minus that number. All right. How much time do I have? 8 minutes.
You have 8 minutes?
Final red difference. Mr. Cummings.
Are you good, Roger? All right, guys. Here's another problem. Let's go again. I see sodium hydroxide, which is a strong base, being added to a solution. All right. It's not identifying what type of solution, so I might have to think through what's going to happen here. All right. But it is a strong sample being added, so I know that it's an intruder. So right away, I'm going to take the strong part of the intruder and add it, this time to the entire solution, since it's not a buffer, and use a normal yield sign. Looking at a normal Bronsted-Lowry interaction, I know that the base wants to accept while the acid wants to get rid of. I need to find the victor of the battle here, but I need mole count. So we're going to do, again, I'm going to change the sig figs on the slide. Sorry. But for the strong base, I'm going 0.2 times 0.5. 0.2 times 0.5 is 0.1. That's my mole count of OH minus. I just multiplied those two numbers, guys. I turned that to liters times 10. All right. For the other one, it's going to be 0.125. 0.125 times 0.500. And we're going to get 0.0625. Do you see the good news? The smaller number will be the one that we subtract, and this time it is the weak dude that's going to lose, because we'll end up with none of him. And this guy over here is going to win. All right? Now, of course, this is what's happening over here, but here's the deal, guys. If the strong wins, nothing over there matters. If the strong wins, everything else is negligible because it's all going to be based off of him. So we're not going to have to continue any stuff over there. All right, you didn't even have to write that. I just wanted to show that, yeah, that's going to happen. But for pH, who cares? He won. Now we do need this number. 0.1 minus 0.0625, 0.0375 probably. I did the wrong number. All right, so 0.0375. And I don't care about anything else because the strong won. Now, this just wants to know pH. All right, now we have hydroxide because life's annoying. But remember, to find the pH of a strong sample, it's just negative log of concentration. That's it. No other steps, no rice table, no nothing. All right. But do I have a concentration? No. We have moles. Moles divided by liters is a concentration. Can anybody tell me what my total volume is here?
325.
Yeah. So it'll be this divided by 0.325 liters. So 0.0375 divided by 0.325 to 3 sig figs is going to give me 0.115. There's a molarity. And in order to find the concentration, the pH of a strong sample is just negative log. So
This is the concentration of OH.
this is the, yeah, it went straight down, all right, on my analytics. So the pOH will equal the negative log of 0.115. So negative log of 0.115. I'm going to end up to 3 sig figs of 0.939. All right. So of course, to find pH, we would just go 14 minus that number. And predictably, since it was a strong base that won, you expect a really high pH, right? You're going to get 13.061.
So 0.939 is pH, right?
Yep, straight across. All right, and it looks like it's negative, but... Gabby, can you show the next slide? everybody else, I appreciate the patience with your brain. I'm proud of you. I hope you are proud of yourself for working so hard on this stuff.
This isn't actually that hard. I thought it was pretty nice. No, in the testing environment, this one's definitely gonna get 95.
All right, if y'all could stay kind of low key as I continue, I'd appreciate it. You got me? Sweet.
Wait, can I stay till the things you want?
Well, I might teach through most of the period. If you so give it to somebody else if you want to stay.
If I don't want to go to my next class, can I stay?
That's a pass. I can't.
English thing.
And no, I can't. I can't make that call. You can watch this video. All right. For those of y'all at home, we're gonna keep going, which sounds terrible,
I'm
right?
in English class. I'm in an English class. But I'm in AP.
Mr. Cummings, Robin's gonna get it for you. I'm gonna stay.
I need her. Your name is on it though.
I know, yeah.
I've never been bullied in my life. How am I supposed to
Of course you've been bullied.
All right, quiet down, please. Here we go. Our new problem says, what is the pH of a 2 molar solution of acetic acid? Now, this question is suddenly not an intruder at all. Look, it's not mixing anything, all right? It's actually asking a question from the first lecture of the last unit. It wants the pH of a weak acid, all right? So, acetic acid. All right, it's asking for the pH now.
Are we on A?
All right, we're on A. So if you remember, whenever we wanted to, and this was one of the introductions of this kind of stuff. If you want to know the pH of a weak acid, you add it to water in a rice table. That's always been the rule. Y'all thought it was easy when I taught it. So we are going to add the HC2H3O2 to water in a rice table. No. It's empty, that's why I'm dying over here. We know that the acid wants to donate, so let's let him do that.
Wait, why is it at equilibrium?
Because it's a weak sample. Yes, please. Thank you, you're an angel. Don't care what your friends say. Okay. And then H3. All right, so there's my normal stuff. And again, this is not new. This is old skills here.
Mr. C, I found stickers back here.
All right.
So this is rice table.
Yeah.
Finally.
Yeah, but that's what we always did. Again, and just to say it again, anytime you're asked to find the pH of a weak acid, you always added it to water in a rice table. All right, that was always the step. All right. So I have an initial concentration here of 2 molar.
I have a question, Mr. Steve.
Yep.
Anyways, will you always tell us to add it into water or whatever?
No, I mean this isn't telling you to though.
Oh, sorry. No, I was. It's 'cause-
Bye, Caroline.
All right, we need to know that our Ka value, all right, is going to be 1.8 E negative 5.
We don't need to change it, right?
That's a given value. No, this was before that happened. All right, and that's the other thing. Thank you again. That's the other thing to keep in mind, guys, and it's one of the challenging things is not to cross the streams on what is what. Yeah, we have a Ka and we're ending with H3O plus. That's all good. This is not hydrolysis. All right. So if we move forward and solve here, all right, we're going to end up with 1.8 E negative 5 equals x squared over 2.0 minus x No, because when you add the acid to water, it's going to produce hydronium. Yeah. All right, so we'll end up with a 0 equals x squared. Okay, we're cross multiplying here. All right, but remember we had to move it over so the sign switched. Plus 1.8 e negative 5x minus something.
Minus 3.6 e negative 5.
Oh, I could have done that in my head. 3.6 e negative 5. So 0 equals x squared plus 1.8 e negative 5x. I'm in my solver now. Minus 3.6 e negative 5. Put in my estimate, and my solver tells me, whoops,
6.01 e negative 30.
that x equals,
Mr. C, Robin asks if she's supposed to give him your number or something. Or
no, I gave her cash.
I give it to him.
No?
Like, he doesn't have to give the name.
I don't know. Tell her if it ends up, what? That's not right. That if it ends up not working, that just fine. I'll eat some more. What do we have? We only have 2 sig figs, right?
Yeah, I put 6.
So it's 6-0.
Yeah, I put 6.0
Yeah, sorry.
e negative 3. Can I do that?
Yep, you can. Same thing. All right. Now this is the hydronium concentration. What does this want? This wants the pH. So if we go negative log of that, we've got it. So negative log of 0.0060. I'm going to get a pH of 2.22.
Wait, Cummings, isn't that the same blue thing we just did in our previous one? Isn't this what we did in our last unit?
Yeah.
So
It's probably step A.
Yeah, this is step A.
It would be. So they just split it in half.
I'm pulling these questions from at least AP exams.
Is
So
that 2.2?
I have questions. So this is all one question, but it's broken down. is what
right,
you're
I've done part A.
saying? Oh, okay.
Is that 2.22?
Yep.
Are you gonna give this in a test, like do part A first, and then what's the answer?
No, that'd be an FRQ.
Oh.
Mostly. Or unless I do a yellow highlighter question that says select both answers. Whatever. All right, so what are we doing next? Part B. A buffer solution. Hey, that's one of the nice ones where they let you know it's a buffer. A buffer solution is prepared by adding 0.1. I can't read that. Is there something right there?
Yes, there's like a. It's like a Z.
Where?
It's like a lightning bolt.
Yeah, it's like a lightning thing. It just means it's just supposed to say liters.
Okay, 0.1 liters of 2 molar acetic acid solution to 1 liter. To 1 liter of 1 molar sodium hydroxide solution. So,
Do we convert to moles?
it's going into an invasion. All right, now we're moving into an invasion. I don't know if I need that pH. I haven't done this problem yet, so let's figure this out together. All right, so part B is moving us into an invasion, so let's read it carefully. All right, it's letting us know that a buffer solution is prepared. We're adding sodium hydroxide. All right, it's sodium hydroxide. That's a strong base. So there's the invader. All right.
Will you ever give us questions that you don't tell us it's a buffer?
Yeah, that we've done one today. But yeah, it could. If remember that problem where they were the same number and they both disappeared?
Yeah.
If I would have given you that same problem, but the ion stayed and then it produced the acid, then they would be buffer because they'd both be in solution. And you'd go Henderson-Hasselbalch.
Okay, I'm gonna tape. I'm gonna ask you what
Buffer is a weak acid or base and its conjugate both in the solution together. Like your blood has carbonic acid and HCO3 minus.
Wouldn't that be like anything?
No. I mean, because we had the example where we completely ran out of one earlier, and we only had the ion left. Here, we'll have to do that later.
Yeah.
So anyways, taking a look here. All right, so we are adding it to, it's acetic acid, right? Oh no, well, it built a buffer. So remember, this is back to the first one. If you add this to a buffer, it doesn't interact with everything. It only interacts with the thing that's trying to fix it. So I'm going to be adding this then to the HAC with a normal arrow. All right, there's the acetic acid. That's what he's going to interact with. Why is he going to interact with that? Well, because the whole point of the buffer is to produce the other item that's in the buffer. So when he accepts this and creates some water, it's going to immediately produce the acetate ion, which of course that's the connection they can produce each other. So now I've got this buffer system set up.
Okay, this might not always be the case, but I've seen this as a pattern. If you start with acidic acid, and then you'll always get acetate at the end, right?
Yep, that's correct. Okay, so we need to figure out who's going to win the battle here. So looking at the problem, it looks like the acetic acid solution was 2 molar and 0.1 liters. So what is 2 divided by 0.1? Should be 0.2. Or times, I'm sorry.
Still 0.2.
Yeah, still up. Well, point. My brain did it right. All right. So again, we're multiplying liters times molarity to get moles. So here we've got 0.2, and actually my sig figs there look like it is 2 sig figs everywhere. So there's the moles there. All right. For the acetic acid, it looks like we were given 0.1 liters of 1 molar. So that'll be 0.1 times 1. All right, so it's just times 1.
Wait, that's moles?
Wait, did I do that? That's something's not right. Oh, I'm sorry. Okay, hey, look. We did all of our math good. But
That's molarity.
I read them backwards. All right, everything is good, but if you'll notice, the numbers for 0.2 are describing the acetic acid, and the numbers for the 0.1 are describing the strong base. Don't make that mistake at home. Make sure you read carefully to get the numbers with the right guys.
That's molarity, right?
No, it's moles.
Moles, yes, that's right there.
These are moles. And molarity is given in the problem. I wouldn't have had to run numbers to find molarity. They just gave me that. I need to compare moles to find limiting reactant. All right?
Shoot, I just think.
Hey, what's the limiting reactant? What's the smaller number?
Oh, wait.
All right? So I'm going to subtract that everywhere. Except on the product side. All right, so that's a bummer. Our strong guy lost. That's not what we wanted to happen. All right, 0.2 minus 0.1 is going to be 0.1. And then we have 0.1 over there.
You divided by liters now, right?
So we have moles. Now, hey, what kind of solution do we definitely have now? Yeah, it's a buffer. Look, that's a weak acid and its conjugate base. Now it's a Henderson-Hasselbalch because they're both there this time. Look, there's amounts of both of them. So we're good to go for it. But, like Annalise pointed out, we have to have molarity, not moles. All right, so I need to figure out what happened here. We added 0.1 liter to 0.1 liter, so it sounds like we're going to end up with 0.2 liters. right, so they're going to be the same, right? They're both going to give us 0.5 molar. Now, hey, they're the same molarity. Do you remember there was a problem in yesterday's lecture where if they're the same concentration, the last part of the equation doesn't matter? But we'll do the whole thing anyway. So in order to find it, it's going to be negative log. All right, does it want pH? What does the problem want? Oh, it wants the hydrogen ion concentration. All right, that's me. Anyways, but we know that pH equals the negative log of the pKa. Or of the Ka, which is going to be 1.8 e negative 5 plus the log. And here's what I'm saying. You don't have to do this part because they're the same concentration, but whatever. We can show it just to make everybody at home happy. The ion over the weak acid. But really, it's just the negative log of that.
Is that you making that sound?
Something.
Oh, I thought it was like you, like your mouth.
So I get a pH I get 4.74 to 2 sig figs. Question doesn't want pH because it hates us.
So we put 10.
Right, to find the H plus concentration to be 10 to the power of negative 4.74.
Equals 1.82.
And to 2 sig figs, it'd be just 1.8
Oh, yeah.
e negative 5.
Wait, isn't that the Ka?
That's a coincidence, yeah.
There's the Ka. There's the
Wait, Mr. C, why is it that that was pH when the pH equals negative log of the equation? The Hasselbeck?
What about it?
Why is it pH and not pOH? I just don't
Well, it would be POH if this was a KB.
Oh, it's just a, yeah, okay.
How do you know which one of you needs it?
Well, it's based off what it's asking for.
Oh.
I mean, everything that what we're dealing with here is an acid. Where's yours? Okay, awesome. Just set it down. You're amazing.
I have my food right here.
Good for you guys.
Yes, I'm starting. Are we doing the next one?
Not right now. I'm gonna have to do another video. My throat's too bad. Hi, thanks for playing. That was awesome.